chi-square testing is a type of test where you want to see if two data sets are independent of each other or they're dependent on each other. And the notation we use is a chi, which is a Greek notation. Be careful that it's not an X. So whenever, if you look at a question, if you look at a data set and you're not looking for correlation, so be careful here, this is not correlation. You're actually looking for whether the two data sets depend on each other. And this is a discussion you should have had when you did correlation. So in correlation, you test for correlation and then but you don't have a clear idea of whether the two data sets cause each other. So it's not a clear set in stone sort of conclusion whether there's a causation between the two data sets. But for chi-square testing, this is what you want to see. Are the two data sets independent of each other or are they dependent on each other? And the way we set it off is we first pick a significance level as well. And this in science, you can research about what significant level does. In examination, you will be given either 1%, 5%, or 10%. And we're going to see where we're going to use this. So this is already given to you, don't worry, but whenever we do chi-square testing, we use a significance level, and this helps you compare your data set to the percentage to decide on your conclusion. So I'm going to go through the process of finding it. So you're going to see the main keyword, the definitions, and I'm going to use this example. But this is the full process of a chi-square test. Usually they might ask you for some of the parts, or they might ask you for the full parts. So the null hypothesis is always the claim that two data sets are independent. So let's say I have this table and it's about the choice of shirt color and the genders picking the shirt color they prefer. So let's say that these are the data sets you have. So what you're going to write for the null hypothesis is that the choice of shirt color is independent of gender. And that's what you always do. And that's what you always do. Whenever you have two data sets, you say that one is independent of the other for the null hypothesis. The alternative is going to be the same exact sentence, but you're going to say that they are dependent. So you're going to say the shirt color is dependent on gender. Next, what you're going to do is you'll have your observed data. So this is the data you're observing. This is what you collected. What's useful to do right now is to do what we call a contingency table. So you're going to add the totals for every row and column. So I'm going to add the totals. I'm going to get these. So add the rows and columns. So 14, 10, 7, and 8, that's going to give me 39, and so on. I'll also have 80, which is what we call the table total. So that's adding up. And it's also a good way to check that you've added the numbers correctly, because the column should add up to 80 and the rows should add up to 80. This column and this row. So now that we have the contingency table, or the observed value table, we need to do what we call the expected frequency, or the expected values. The way we find the expected frequency is similar to you doing probability from a table, so they are exactly linked, but I have a different formula here. In order to find the expected value, so these are what you'd expect if your data is independent. And what you're going to do is take your total from the row, multiply by the total from the column, divided by total from the table. And I'm going to show you an example. So in an internal assessment or in a longer example, practice example, you are expected to find the expected frequency for every single cell. But in an exam, they'll only ask you to find one. So for example, if they ask you for male and red, okay, so what you want is male and red, what you want is this value. So what you're going to do is you're going to take the total from the row, so you're going to take the total from here, and you're going to take the total from here, you're going to multiply them and divide them by the table total, which was 80 in this case. So the total row times total column divided by 80. And that's going to give you the expected value for this cell. And you're going to repeat the same thing for everything else. So if we go back to the previous slide, so for the male red, so this cell, ignore this 7, ignore the observed data, you're going to write the expected value. So you're going to take the total of the row, which is the column, which is 13, multiply the total of the row, which is 39, divided by the table, which is 80. And that should give you the expected frequency, which I'm going to reveal later. An alternative way using probability is to say, well, I have 13 out of 80 people that picked red, multiply by, I have 39 out of 80 male that I have, and this will give you the probability value. But in order to get an expected number, you're going to multiply this by 80. And what's happening is things simplify and you'll end up with this formula instead. So it's up to you which method you want to use. So if I continue with this method, I'll do the same thing for every single cell. Total row times total column divided by total table. You're going to get all these values here. Now, next questions will ask you for degrees of freedom. So degrees of freedom tell you, as it says, it's how much freedom you have in your data. The bigger the degree of freedom, the more freedom there is for your results to move around. That's a very rough way of translating it, but the degrees of freedom, you'd prefer them to be small. If you have a degree of freedom of 1, there are other things that you have to do, but that's not something to be concerned about in an exam. So degrees of freedom, you'll just follow the formula. You're going to take the number of rows you have minus 1, the number of columns you have minus 1, and multiply them. So without the total. So I have 2 males, 2 genders, so I have 2 minus 1. I have 4 shirt colors, so that's 4. 4 minus 1, and then you're going to get 3. Okay, so that's your degree of freedom. As for the chi-square, you're going to follow the steps that I'm going to show you, and to find the chi-square value, you're going to use the calculator for this. So you're going to go to second and then matrix. Do pause the video to see what I'm doing because I'm going to go fast. You're going to go to edit, you're going to press enter, and you're going to enter your dimensions. So in our case, it's 2 by 4. So once I have the 2 by 4, I'm going to enter my data sets in here, and then that's it. If there's data here, already erase it and just add the data. So that's the first step, and then you're going to go to stat, you're going to go to test, and you're going to go all the way down, and you're going to see chi-square test here. Don't pick the other one, that's the goodness of fit test. You want the chi-square test. So enter here, and what you're going to do is enter the matrix here. If it was cleared, like there was nothing here, just go to second matrix again, and then press on the one you have. Just stay on the names tab. So you're going to press on A. For expected one, what the calculator will do is that it will give you the expected table. So if you don't want to calculate the full expected table, the calculator can do it for you. Again, if it's cleared, you can do the same thing. Pick any empty one. It doesn't matter. The calculator will do it for you. Even if this is filled, it's going to overwrite it anyways. And you're going to press on calculate. And this is the page you're going to get. So we are going to get these values. The first value is your chi-square value. So our chi-square value is 2.13 to 3 significant figures. We have our p-value, which I'm going to talk about in a bit. So finally, once you're there, what you're going to do is 2 different things. Either compare your chi-square to what's something called the critical value, or compare your p-level to something called the significance level. So we mentioned the significance level in the beginning. So what you're going to do is the critical value is always given to you in the question in an exam, and the significance level is also given. So for this question, the critical value is 7.815, and the significance level is 5%, but you're going to use the decimal value, which is 0.05. What you're going to do is compare the chi-square value with the critical value, or compare the p-value with the significance level. So what we have is chi-square versus critical value. Our chi-square is 2.13, and compared to the critical value given in the example, 7.815, it's less. If it's less, then you have to accept the null hypothesis. That's the condition. If it was more, then you reject the null hypothesis and you take the alternative hypothesis. As for significance level, we do the same thing, but it's the opposite. So my p-value is bigger than my significance level. Again, significance level given in the question. If it's bigger, we accept the null hypothesis. If it's less, we reject the null hypothesis. So you just need to remember these facts, these conditions. So we accept the null hypothesis, or we can say that there's no sufficient evidence to reject the null hypothesis. Therefore, the choice of shirt is independent of gender. And that's how you conclude a chi-square test. You have to make a proper conclusion and not just find the chi-square and stop there. So this is the full process. Hopefully it was useful. There are other videos I have on chi-square testing where I go into a bit more detail on these, but this is a shortened one.